The goal of routing is to determine the shortest path between nodes. Like many things in life, there is often more than one solution to a problem. Distance vector was one, link state is another, which is the focus of this video. The basic idea behind link state is rather simple. There are two phases involved. Phase 1 is called reliable flooding, where to begin with, each node knows the cost only to its immediate neighbors. But finally, each node knows the entire graph or the network topology. Once you have the entire graph, route calculations are rather straightforward. So this is part of phase 2. Each node can then use well-known and efficient algorithms like the Dijkstra's algorithm on the graph to calculate the optimal path to all the nodes. Phase 2 is rather simple. The challenge is often in phase 1. So this is what we will focus on mostly. So tell me, how can one go from this state to this state? So this name should give you a hint. Let me give you another hint. Have you ever told a juicy tidbit to your friend and next thing you know, everyone in the class knows about it? And similarly, if someone else has a juicy gossip, in no time you get to know. So what's happening there? Use that to go from this initial state to this final state. Each node, if it somehow conveys its neighborhood information to all the nodes, this neighborhood information is henceforth called link state. So A will tell others that it is connected to B and to C at a cost of 1 each. So this is the neighborhood information that A will tell all the nodes in the topology. And if every node does this, finally A will know the entire topology information. One point I wish to emphasize here is that this information has to be conveyed reliably. This is very important. Why? Suppose this was the original topology connecting A, B, C, and this link has failed. Now A detects that this link has failed. So as far as A is concerned, the topology it thinks is this. So this link is not there. Now let's say it tried conveying this information to B, but somehow that packet got lost. You are not reliably conveying this. Now what does B think? B thinks that this is the entire topology. So to read C, B will send packets here, whereas to read C, A is going to send packets here. So the packets will now get stuck in a loop, which you don't want. So let's get back to the problem of how does a node convey this link state information to all the nodes in the topology. If we address that, each node can then have the entire topology information. So what are your thoughts? Suppose I were to tell you the IP addresses of all the nodes in the given topology, then can you establish connections with all these IP addresses and thereby convey whatever information you want to convey? Well, that was a trick question. In order for you to route the packets to the correct node, how are you going to send them? I mean, there is no forwarding table. In fact, that is what you're trying to figure out as part of this routing process. In reality also, a given node often does not know what are all the other nodes as part of the topology. So how to solve this problem? The flooding is what is employed. Simple idea, you tell your neighbors the information you want to send and ask them to pass it on to their neighbors, so on and so forth. Finally, everyone will get to know. So here it is. A has some information to send, so it sends it to its neighbors B and C. C, on receiving this information, since it received on this interface, it doesn't make sense for it to send it back to that particular neighbor. It forwards it to its other neighbor, which is B. Similarly, B, when it receives this packet, it is going to forward it to C. Now, if your logic is dumb, what C can do is once it receives a packet from B, it may think, okay, this has come here, so let me forward it in this direction. And similarly, when B received a packet from C, since it came on this link, it can forward it on the other link. And now the process is kind of going to repeat and these packets are stuck in a loop. So flooding has to be done with lot more care. If you thought flooding was rather straightforward, the next few slides will dispel this notion. Often when you implement, things turn out to be a lot more complicated than the basic idea. So we are going to focus on how to implement flooding reliably, what features should this flooding approach have, and In this process, you will see certain problems and how to address those particular problems. As I mentioned earlier, reliability is very important when you convey this information. So when A sends a packet to C, it has to ensure that this packet has reached C reliably. And we have already seen enough reliable protocols. So there are mechanisms to achieve reliability. So I won't get into more details there. We already saw the looping problem before. We need to avoid that. But more importantly, we need to minimize the number of messages exchanged to achieve flooding. Ideally, if this were the topology, on each link, you just want one message to go. This may not always be feasible, but that is what we will like to achieve. So how would you avoid this looping problem? Think of a solution. Apart from the looping problem, there is really no reason for B to send a packet to C after it hears from C as well as A. Even this you want to avoid. This will minimize the number of messages exchanged. So how can all this be handled? Rather simple. You need a mechanism to detect duplicates for which if packets have unique IDs, based on this, you can detect whether a packet is a duplicate of what you have already seen. If it's a duplicate, you can thereby act accordingly. A simple way to act is to maintain state. Let me call it send flags. So let me give an example. Suppose when B heard from A a packet with an ID, let me call it X for now, it knows that this information has to be sent to its neighbors C and D. So it's going to kind of put a tick. But even before it acted on it, let's say it also heard from C, the same packet with ID X, in which case it knows it doesn't have to send it on C. So it will change the tick to cross. And after this, it just needs to send it out to D. So this doesn't happen then, only this happens. We are not done yet. This is in fact the simpler problem to handle. There are more complex issues. In a practical setting, topology changes, in which case this new information should precede the old information. Again, let me give an example. In this topology, let's say the cost of 3 has changed from 3 to 6. But prior to this, A has sent out information that A to B cost is 3. To both nodes B and C. By the way, it would have also sent A to cost C is 1, but for now we will ignore that. So C received this information. B also received it. Right after this, let's say the cost changed to 6. So A is now sending new information saying that A to B cost is 6. So that information has now reached B and it has also reached C. But prior to this C acting on it, let's say C had already sent this information to B. So B has received this first. After this, it has received this A to B is equal to 3. So should it act on this or should it act on this? How does it know which one is the newer information? How would you solve this problem? Again, the solution is not difficult. One can use sequence numbers, and these sequence number also uniquely identify the packet. So this is with reference to the previous problems where I mentioned you need a unique ID for a packet to detect duplicates. So the sequence number can act as that as well. And what happens is that each node, when it sends a new information, it is going to increment the sequence number. That way, in this particular case, this message is going to have, let's say, sequence number of X plus 1, whereas this will have X. So B knows to act on this and discard this particular message. If you introduce sequence numbers, what can potentially go wrong? We have seen this before. Well, what about if the sequence number wraps around? So how would you handle this? Again, a simple solution, use a very large sequence number space, 32 bits. Unlike in earlier cases where wraparound can still happen when you use such a large sequence number, it is much less of a problem here because these linked state information messages are sent not so often. Let's say if they are sent once every second and you're using this much sequence number space, how much time will it take for your sequence number space to wrap around? Basically 2 to the power of 32 seconds, and if you do the calculation, this turns out to be roughly of the order of 136 years. This router will likely die before hitting wraparound. We are still not done. More issues. What if you have sent a packet with sequence number 4 but it got corrupted and this had become, let's say, 128. What problems can it cause? Quite a few problems. Let's look at it from the perspective of a node A. So the node A received the sequence number. So it stored the information, some linked state information specific to this particular sequence number. But this is a corrupted sequence number. Now the source, the original generator of this linked state information, now has sent another message with sequence number 5. And now when this comes to this node A, what will it do with this new sequence number 5? Will it accept it or will it discard it? It gets discarded, right? Because this has a bigger sequence number than this. So this packet gets discarded. Not only that, any other sequence number that is being sent will get discarded till you hit this 128. Big problem. How do you handle it? Well, you should use checksums to the extent possible so that you can detect such corruptions, but checksums are not foolproof. So the way to handle that is each entry that is stored at a node is aged. For example, this entry will have a lifetime. Let's say you set it equal to 10 seconds. After this time, it is going to be cleared out. So it may happen that during this time, you may reject all these sequence numbers that are coming, but once this entry is removed from, you will act on the sequence numbers that are coming later. So finally, you will get to the right state. Not done still. What if a router crashed and came back up? What sequence number should it use? Now you know why network researchers are in business. Lot of subtle issues. When a router crashed and came up, it will have absolutely no idea on what sequence number it stopped at. So for all practical purposes, you might as well start with any sequence number, in which case you might as well start with sequence number 0, and that is what it does. Naturally, if it starts with a sequence number 0, the older information that it sent may still be in the network topology, in which case nodes may not act on this newer sequence number 0. So for this, it is very important that this older information not stay in the network for long, because it will interfere with newer information. So for this, a technique which we have already seen before is to associate each packet with the time to live, and once this time to live reaches 0, you're going to remove this particular packet. So specific to this router that crashed, and if it had stayed down for a really long time, hopefully all this older information would have cleared out, in which case sequence number 0 will work fine. But if this router crashed and came back up immediately, then this older information, there's a good chance that it is going to stay in the particular network, in which case it will get discarded after some time, based on which this particular sequence number will come into action. One optimization this node can potentially do is, if this node were to hear its own packet, this corresponding to this older information, it can look at the sequence number and it can increment the sequence number within this packet and reuse it. So in other words, it starts out with 0, but if it were to hear some old information of itself, it is going to look at the sequence number and it will increment that sequence number and start using this. Now we are done. So let's put it all together. So this is again the protocol aspect. As we have seen before, for a protocol, you need to cover what message to send. We call this the linked state packet. So what information should it contain? What to do when you receive this linked state packet? This is the action at a node. And when do you send these linked state packets? These we call updates. So this is the information that is carried within a linked state packet. So this packet should definitely contain the ID of the node that has generated this particular packet, not forwarded, generated the packet. And this should also include information about the linked state of the node, that is the neighborhood information, the list of neighbors and the cost to each. Based on these two is how a given node generates the graph information. So this is necessary for calculating the routing. Lot of the other practical problems that we have seen are handled via the sequence number and time to live, which also needs to be carried as part of the linked state packet. So what does a node do when it receives a linked state packet? Let's look at it from the perspective of node X and node Y. Suppose node X were to receive a link state packet generated by node Y. Notice that Y need not be X's neighbor. It had come through some neighbor of X, but it was generated by someone else. So first thing the node X does is whether it had heard from Y before. Suppose it did not hear from Y before. What should it do? Basically, it needs to store the information because this is new information that it is getting. And as I mentioned earlier, it needs to time each of this entry. So it starts an aging timer. What if X had already heard from Y before? What should it do then? Then it should compare the sequence number of this new packet with the sequence number that is already stored. If this sequence number new is greater than sequence number old, what should the node do? Override the old link state information, refresh this aging timer and forward to the required neighbors. You don't have to forward to all, you will have to forward to subset of the neighbors depending on where you got this information from, like we talked about earlier. What if the sequence number new is less than the sequence number old? What should it do? You discard the received packets because you got some outdated information. So the next question is, when do you send these link state packet information? Notice that flooding leads to a lot of traffic because this link state packet is sent to every node. So you should avoid flooding to the extent possible. Like before, whenever the link state information changes, you naturally need everyone else to know the information because the graph has changed. So in which case you have to flood. These are called triggered updates. We also need to support periodic updates. These need not be sent often because of this flooding issue, as I mentioned. In this particular case, you use very long timers of the order of hours. If you implement those three aspects of the protocol, each node now is going to get link state packet from every node and thereby it will have the complete graph information. Once you have this, you can use Dijkstra's algorithm to calculate the shortest paths to node and you're done. So here are a few points to note specific to link state algorithm. There is no problem of this count to infinity looping because each node has global information. However, it is possible to have transient loops when topology changed and you're in the process of getting the new topology information. Again, convergence in link state is very fast because you have global information. However, link state suffers from scalability problems because you are flooding the entire network and also the computation and the amount of information you have to store at each node is high because you have to maintain the entire graph information, which node has which neighbor, so on and so forth. So this flooding can be handled to some extent by setting periodic timers to hours. And this information is handled through the use of areas, which I will cover a bit later. Now is a good time for a break. Once you're back, we will cover a protocol called OSPF, which implements link state algorithm. OSPF, which stands for Open Shortest Path First, is a very widely used interior gateway protocol. You must be wondering, what is this interior? We will cover this shortly in an upcoming video, but for now, assume that this is a protocol that is used within a routing domain. This has more or less replaced RIP because it converges really fast. Unlike RIP, which operated at the application layer, OSPF operates at the network layer where the OSPF information, these link state packets, are encapsulated within IP datagrams with a protocol number of 89. So in other words, when this IP layer gets a packet, within the IP header, if you see that the protocol number is 89, you pass this to the OSPF process, which also operates at the network layer. Since I mentioned earlier that reliability is very important, so OSPF implements reliability itself via checksum as well as ACK mechanism. OSPF supports many features. Example, it supports authentication. That is, a router accepts messages from other routers only if it has authenticated those routers. This is very important to have. What if a malicious router advertised to other routers that it can reach all the IP prefixes in the internet at cost zero? What's going to happen? Everyone will start sending traffic here and It'll just drop them and that's it. Internet has been brought down. It also supports additional hierarchy. Remember I said earlier scalability is an issue with link state. So it tries to make it scalable by introducing an additional level of hierarchy through areas. I will touch upon this briefly. It also supports load balancing, by which I mean if there are two equal cost paths to a given destination, it will try to load balance traffic along both paths. Again, this is feasible because you have global information about the entire topology. OSPF as such is a very complex protocol. It has many types of packets and a lot of action based on the type of packet. I'm going to provide a very high level overview. The relevant concepts we have already covered. So here is how OSPF handles scalability. The entire routing domain is divided into areas. So here we see area 0, area 1, area 2, area 3. Area 0 is a special area that is made up of the special area border routers. These area border routers basically interconnect non-backbone areas with the backbone area. Each area is definitely served by one area border router, sometimes even more. For example, area 2 is being served by two area border routers, this and this. It is easier to understand areas if we chart out the path taken by a packet. By a packet here, I mean IP datagram, not a link state packet. Suppose a host A in area 1 wants to send a packet to host B in area 3. The path taken by this packet is that it goes from this particular host to the area border router that is serving this particular area, and then it crosses the backbone. In this case, let's say it takes this path, and once it gets into area 3, again it finds out a path from this area border router that is serving area 3 all the way to the particular host. So how does this help scalability? Basically, the link state algorithm that is being run in an area, the advertisements do not leave the particular area. So for example, if this router is generating a link state packet, this is sent to all these routers and it is not sent to any other router. So the flooding happens only within an area. But then how do these routers within this area know how to reach other networks that are part of other areas? So this is handled by the area border routers. So what an area border router does is it is going to summarize whatever information it has learned within an area by participating in the link state algorithm as part of the area, and it interjects this information into the other areas. For example, let's look at this area border router. So this area border router knows the topology of area 1. What it does then is it participates in the link state algorithm of area 2 as well as area 0. And when it participates, let's look at what it does in area 2. It generates a link state packet where it claims that it can reach all the networks that are part of area 1 at a cost of 0. So these other routers, if they want to send a packet to any network in area 1, know that they can reach it via this area border router. They don't know what the topology is within area 1, but they know how to reach particular packets in area 1. So this area border router does the same even within area 0 as well. That is how these other border area routers receive that information, and thereby they will summarize that information and inject it into their respective areas. Let me also mention this point where an area is served by two area border routers. So this will hear information, it is going to interject the area 1 information. Similarly, this also may have heard this information from this router and maybe via this router, so on and so forth, and it will also interject information about area 1. Now a router here may decide to go via this router or this router based on whatever is the shortest cost. In this particular case, maybe it makes sense for it to go via this area border router. Often when dealing with areas, the scalability becomes more important than the absolute shortest path. For example, if these two routers were indeed directly connected, you will not send packets over this path because according to these areas, this router will not advertise its link state information to this particular router. So that's with respect to areas. As long as you got a high level picture of how areas work, that's good enough. So here is the packet format of OSPF. All OSPF packets have a common header that is represented here. So the first field again is the version field. This, if you set it equal to 2, corresponds to OSPF version 2. There is in fact OSPF version 3 which handles IPv6. As mentioned earlier, there are many types of OSPF packets. So this specifies what is the type of packet. So there are packets called hello packets. For example, these packets are exchanged to discover other OSPF enabled routers. These packets also act as the keep alive messages so that you know if your neighbor has failed. So type 2 is a database descriptor packet. So they maintain databases. Let me not get into this. A router can request link state information from other router, that is done through request, and link state update is like a reply or a link state update that is generated periodically. As I mentioned earlier, acknowledgements have to be supported as part of OSPF, so this is the acknowledgement field. Following this is the packet length. It includes the header also, how big is the OSPF packet. Router ID is basically the generator of this particular OSPF packet. This is typically set to the IP address of the router. Remember, a router can have many interfaces and thereby many IP addresses. You can set it to the smallest IP address. To handle areas, these also specify the area ID. Checksum again I mentioned is important, so that's also included. And OSPF supports authentication. Within authentication itself, there are different types, whether you want to do authentication. If you don't want to do, you can set it equal to 0. If it's a simple password authentication, or whether it's a cryptographic authentication. The field following this will carry some authentication information. For example, if it's a password authentication, you may specify some password information here. Following this is the message body, which varies depending upon what type of packet it is. So here is an example of a link state update packet. So this follows the header that I have described earlier. So here you specify the number of link state advertisement followed by the link state advertisements themselves. This link state advertisement itself has a header, and here is the header. This advertisement has an age. This corresponds to the TTL field as I have mentioned earlier. This link state advertisement itself can have different types, whether it is advertising a router reachability or whether it is advertising a network reachability, so on and so forth. And link state advertisement also has a link state ID who is advertising the sequence number that we have talked about, again a checksum, and the length of the packet and the body, which again is a function of type. All this is just to give you a flavor of how OSPF looks. I don't want to get into more details than that. Now that we have seen distance vector as well as link state, let's compare them both. In distance vector, each node talks only with its directly connected neighbors, but it tells everything it has learned. The problems we saw there are the formation of loops, the count to infinity problem, and the fact that this distance vector suffers from slow convergence. On the contrary, in link state algorithm, each node talks to all the nodes but only states information about directly connected nodes. This, because you have global information, has very fast convergence, but it has scalability issues, which to some extent are handled via areas. So here is a summary. So link state routing is another approach to routing based on reliable flooding. It provides very fast convergence, but it can pose some scalability problems. OSPF is a popular standard that implements link state routing. Both RIP as well as OSPF fall under this category of interior gateway protocols. Up ahead, we will cover an exterior gateway protocol. This also goes by the name inter-domain routing.